Hi everyone! In this video we will present a 3 Degrees of Freedom robot. This industrial robotics project involves mechanical, electrical, and software development. Hope you enjoy it! For the mechanical part, we will show you how it was built. At the electrical section, the circuit will be described, so as the servo motors that were used. At the software part, we will show you how it was controlled and the design of the user interface. You will see the prototype operating in manual and forward kinematics mode. Also, you will see the robotic arm making some minimalistic artwork. So, let's begin! Let's start from the base. It was designed in SolidWorks, having in mind that the raw material was going to be a MDF panel. Slots were placed considering the location and dimensions of the motor at the base and the input and output connections. A slider was added to close the back of the box. These pieces were manufactured using the laser cutting machine.
A 3D printed piece was designed to fix the base motor. Screws were used to place it or remove it when needed. The lateral and frontal faces of the box were also fixed by a nice 3D printed cover with the team's name on it.
The end effector was designed based on the compatible dynamical links. Since the purpose of the robotic arm was to make some art, a maker holder was added at the top. To allow different sizes of makers, the holder had 2 holes to insert set screws.
Now, let's move to the electrical part. The robot's joint correspond to Dynamixel AX12 servo motors. They can be connected in a daisy chain. The running degree goes from 0 to 300 degrees, with a resolution of 0.29 degrees. The recommended input voltage is 11.1 volts. They have a AT-MEGA8 microcontroller which communicates through half-duplex UART TTL. The communication with the Arduino is established through the serial port. In order to use the Dynamixel library in Arduino, a 3-state buffer needs to be added to the circuit. A homemade shield for the Arduino was used to consolidate the whole circuit. The data, voltage, and ground cable of the first servo motor was connected directly to the shield.
The user interface of the robot was programmed using Python 3 and the following open source packages: PyKitty5 for accessing multimedia and easy interface resources, PyOpenGL for accessing the graphic resources available in the computer, NumPy used for matrix operations, and PySerial for accessing the serial communication ports. The interface runs on 3 main application loops. The main thread handles the widget creation, animation, and event handling. In this main loop, all the user inputs are managed. Additionally, most of the user interface outputs, like text boxes and animations of the built-in widgets, are also handled. Another thread supports user inputs using the keyboard to move any of the joints in a positive or negative direction, or to increase or decrease the resolution of the joints' movements. Finally, a 50 Hz thread of the program displays a virtual twin of the robot arm. This is accomplished using a 3D drawing of the links. Each point of the 3D object is linearly transformed using homogeneous transformations calculated on the DGM and then drawn using OpenGL library.
The Denavit-Hartenberg parameters were obtained to compute the direct geometric model. Here is a picture of the robotic arm and a table of its DH parameters. All thetas are variable since all the joints are of revolute type. You can see from reference frame 0 to 1, the axis of the joint is rotated 90 degrees counterclockwise on the x-axis, with an offset of 32 mm on the zeta-0 axis. The next 2 joints' axes are aligned and have an offset of 93.5 mm and 155.6 mm, corresponding to their link's size, with no angular rotation.
During the development of the project, I noticed that there are critical parts that are important to have a good or a bad behavior of the robot arm. For example, the mechanical part. I noticed that without a proper base and a good holding of the structure of the robot, we could have issues when the servos are acting. And also a good design in the end effector was really important because at the end this determined the position of the tool. And without a proper holding, we could have issues and increase or error. And finally, the project helped me to understand better how to get the DH parameters and also how to identify and how to design the kinematic diagram and how those things influence in the movements of the robot.
One of the things in which we struggled the most was the serial communication between the computing hosting the user interface and the microcontroller in the robotic arm. After several attempts, we realized that our problem was mainly because of the overflow in the buffer of the microcontroller. So we realized that we needed to include a timeout between each of the messages sent by the computer. After doing that, we were very satisfied to see that the results in the physical system match very closely the ones that we saw in our DGM calculation.
One of the conclusions I have about the first phase of this industrial robotics project is that having good basis about the theoretical part of industrial robotics, I mean working with the DGM and programming this function of MATLAB, helped us to have a really smooth transition to constructing a physical model. Also, I would like to add that it was a challenge for the mechanical part to consider all the specifications. I mean, working on having the cables protected, also having all the labels. And I understand it now since all the industrial robots need to have these standards or higher.
In this project, a fully functional 3 degree of freedom RRR type robotic arm was designed and constructed, along with a user interface that allows to manually control the position of each and every one of the servo motors used, computing at the same time the TCP position with respect to a base reference frame. For the future in this project, the implementation of the inverse geometric model should allow us to control in a more smooth and precise way the TCP positioning along any trajectory.